Hello everyone, and welcome back to another video where we are going to be evaluating this nice little integral that I found kind of regrettably while scrolling on Instagram, mainly because I spent too much time on that and the fact that I was on Instagram. But anyway, moving on from that, let's get cracking. What we're going to do to evaluate it is going to be to focus mainly on the exponential right here, and mainly how, or really an alternative way to express it, that way we can apply Glasser's master theorem. So popping right in, we have, or really popping out a minus a, that'd be a better way to say it. Let's factor out a minus a, shall we? We have, or which leaves an x squared plus a b over a times 1 over x squared right here. And one thing that we can do next actually is to complete the square right here. So just to complete the square with these x squared terms. And what that's going to do is the following. It's going to get us, well, in x minus the square root of b over a times 1 over x all squared. But then we also have to, actually do the completing the square bit of the completing the square. So what we're going to have then, whenever we FOIL all this out, is an additional minus 2 square root b over a. The x's will cancel. So to compensate for that, we're going to have to add an extra factor right here, a positive, so plus square root of b over a, and there is a 2 out front. And let's not forget about r minus a. That's going to be distributed to all of this right here. So now that we have simplified it at least a little bit, let's substitute that back into our integral. Our integral then is still the integral over all real numbers, but we have e to the minus a times x minus square root of b over a times 1 over x squared, and then minus 2 square root ab. You might be wondering how the a got up right next to the b, and that's just because whenever we distribute this a right here, we also have a square root of a in the denominator, and that will just simplify to being a square root in the numerator, dx. So what we're going to do next is one small simplification thing before we get into the main theorem bit of this video. So we're just going to factor out this factor of e to the minus 2 square root ab, leaving us with just the integral bit. So the integral over all real numbers of e to the minus a, and then x minus the square root of b over a times 1 over x, that all squared, and then dx. And now is the part of the video where we pull out the theorem. So scrolling on to the right, what we have is something called Glasser's master theorem. And what this theorem states is that if we do, say, some substitution, u is equal to, say, some x minus some a naught, and then minus some sum of just a collection of 1 over x sort of terms. So really it's from n equals 1 to, big N, just some number of terms really. Absolute value of an, and then divided by x minus bn. And what this essentially states is that the principal value of the integral over all real numbers, let me scroll down, the principal value of the integral over all real numbers of f of x dx is going to be equal to the integral over all real numbers, or pardon me, the principal value still. So the principal value of the integral over all real numbers of f of u dx, that is a dx, not a du, just for reference. So the way we can actually apply this to our problem right here is effectively to, invoke this. And the reason we can is because, you'll see that we have this term right here. It's an x minus some constant times 1 over x. And very clearly that fits under, the criteria in Glasser's master theorem, because, we have, you just let that equal 0, and then let that right there equal square root of b over a. So rather clearly our integral, I guess, fits under the conditions for this, and we can just, evaluate it as such. So what we have then for this integral part is just the integral over all real numbers still, or at least the principal value of it is equal to the other one, but anyway, is e to the minus a times u squared, and then times dx. And we can just evaluate this with respect to u effectively, I believe, so we can change this right here. And this integral right here is rather, it's not terrible to solve. It is just the Gaussian, just with an extra a right there. So in order to not just hand wave and let an answer just kind of appear, I'll actually, I should do some sort of substitution. So I will let v equal the square root of a times u, making this in the integral over all real numbers still, but we have e to the minus v squared now, times dv, and then because of this factor of 1, or this factor of the square root of a, we're going to have a factor of 1 over the square root of a out front, meaning that this right here is just going to be equal to the square root of pi over a. And well, we've evaluated all the integral parts, so we just gotta put everything together. Just kind of yoink this bit from up here and throw it down here. And what we find is that our total integral, so everything, is equal to the square root of pi over a, and then times e to the minus 2 square root of ab. And that right there is the answer to our integral. What is kind of cool to see actually is that whenever you plug in 0 to this, so let b equal 0, this whole term right here just completely disappears, which is what you would expect because it should reduce the normal Gaussian in that case. So I hope you all enjoyed this video. Apologies if some of the audio is messed up. I'm trying both a new recording software and a new microphone in this video. But yeah, anyway, thank you all for watching, and I'll see you in the next one. Bye!